Let's see an example, which is a quite familiar example by this point, which involves the mixture of two normals. Let's consider our old friend, the two-component mixture of two normal distributions, denoted by P times the n mu1 sigma 1 squared plus 1 minus P of n mu2 sigma 2 squared. The probability density of an x is given by P times f1 of x plus 1 minus P times f2 of x, where f1 and f2 are the normal mu1 sigma squared 1 squared and the normal mu2 sigma 2 squared densities respectively. The unknown parameter in this case are the proportion P and the mean and variance of the two normal distributions, so mu1, mu2, and sigma squared 1, sigma squared 2. Given a random sample x of size n, the likelihood of theta, given the observed data, which are the x values that come from the mixture normal, is given by the product over all n's of P times the density of the first normal plus 1 minus P times the density of the second normal. You can see if you take the natural log of this, then it's going to be give you the sum over all n's of the log of the summation. And the log of summation is not really easy to work with. So for this example, instead of maximizing the log likelihood of the observed data, so the observed data log likelihood, let's try to implement the EM algorithm and to estimate theta. We will introduce the latent variables, in other words, our missing data, y1, y2, all the way up to yn, where yi denotes the unobserved membership of the ith sample, and yi is either 1 with probability p, denoting that the ith sample comes from the first normal distribution, or 2 with probability 1 minus p. So in this case, the ith sample comes from the second normal distribution. You can see that in this case, conditioning on yi equals k, where k is either 1 or 2, xi is going to follow a normal distribution with mean mu k and variance sigma square of k. The complete data likelihood given the y's and the x's is thus given by this equation over here. So it's essentially the product over all n's of pyi. So p, the probability that it comes from a particular class, 1 or 2, times the corresponding normal density. And if you take the natural log of this, you get the complete data log likelihood is the sum over all n's of log of pyi divided by square root of 2 pi sigma yi minus xi minus mu yi squared divided by 2 sigma squared. And you can see this case, it looks a lot neater compared to the case where we work with the observed data log likelihood. So what are the E step and the M steps for this example? Let's recall that in the E step, we want to compute Q of theta and theta old. In other words, the conditional expectation of the log likelihood, the complete data log likelihood, conditioning on the observed data and theta old. In this case, our observed data are the x's, and the missing data is our y, which is the membership of each I. In our case, this conditional expectation, where our q is equal to the sum over all n's of this thing inside. You can see that for each n, because we're taking an expectation, we need to consider each possible value and the corresponding density. In this case, because y is discrete, we consider the corresponding probability. So for each I from 1 to n, the expectation is the complete data log likelihood, plugging in that y is equal to j. times the probability that yi is equal to j given xi and the old theta value. And the conditional distribution of yi, the conditional probability that yi is equal to j, that is, the ith observation comes from the jth group, given the observed xi and the old theta, is given by the joint distribution divided by the marginal. And if you expand that, that's going to be equal to the old pj, that is the probability that a random sample comes from the jth group in the last iteration, times the normal density given the old mu j and the old sigma squared j, divided by essentially P1 times F1, which is the first normal density, given the old parameters, plus P2 times F2, given the parameter estimates from the last iteration. So in our case, we have two possible groups. So we knew that we can denote the first group to have Pj, which is P1 equal to P, and the second group will have membership probability 1 minus P. However, this is generalizable to the case of K, which is larger than or equal to 2 classes. So that was the E step. In the E step, we tried to get this Q theta and theta old. In the M step, it will involve maximizing over all possible thetas, this Q theta, theta old we got from the last step. This can be done by computing the partial derivatives of Q with respect to each parameter. So with respect to P, mu1, mu2, sigma 1 squared, and sigma 2 squared. And setting each of the partial derivatives to 0 and finding the roots, we'll be able to find what value of theta maximizes the conditional expectation of the complete data log likelihood. So after some algebraic manipulation, we can find that the roots are given as follows, where Pj nu is going to be the sum over all n's of the conditional probability that yi is equal to j, given xi and theta old, divided by n. So essentially the mean of these conditional probabilities for over all i's. For the jth group, mu j nu is given by the fraction of the sum of each xi times the conditional probability that the ith sample comes from the jth group, given xi and theta old, divided by the sum over all i's, the conditional probability that I comes from the jth group, given xi and theta old. Sigma squared u is also a fraction, where instead of having the product of xi with the p over here, it instead have the square deviation between xi and mu j squared times, so it's the product of xi minus mu j squared, and the conditional probability that I comes from the jth group, given the observed data and the old theta. So let's try to conduct a simulation study where the true P, which is the membership probability that someone comes from the first normal, is 0.2. And the mean and standard deviation of the two normal distributions are given over here. So mu1 is 3, mu2 is 5, and two variances are both 1. We're going to simulate a data set containing a sample size of 1,000 from this mixture normal. So just like before, we first specify the true parameter in the sample size. And then we first generate the membership category, so our latent Y, from 1 and 2, indicating whether each of the 1,000 observations come from group 1 or group 2. And then for the corresponding group, we generate X from the normal distribution with the corresponding mean and variance. What we're going to do is to implement the EM algorithm on the dataset we just simulated and try to find the MLE of theta. So we first need to specify our initial values, that is our theta old at the very beginning. We're going to iteratively update this with the theta new that maximizes the Q in each iteration of the EM cycles. So let's set the initial value of P old, to be equal to 0.5. Let's set the initial values of the two mu's of the two normal distributions to be equal to 0 and 1. Additionally, let's set the variances of the two normal distributions to be both equal to 3. You can see that here I purposefully set these initial values to be different from the true parameters. Let's see whether the EM algorithm can help us recover the true parameters. But first of all, let's create a function for computing the conditional probability that ith observation yi is equal to j, indicating that the ith observation comes from the jth group. J is either 1 or 2, given xi and the old theta. Recall that this is equal to the joint divided by the marginal. This function will be called in each iteration when we try to find the current maximum of Q theta, theta old. So let's call this function py. And this function takes input x, which is the observed x values, which is going to be a single value, p, which is the probability that this observation comes from the first class, so j equals 1. We know that the other one is 1 minus p. And then it will take two vectors as inputs, which are mu's and vars. And these are vectors of length 2, where each entry are the corresponding means or the corresponding variances of the two normal distributions. Inside this function, let's first compute the numerator of this expression. And as you can see, because we have two possible j values, j equals 1 or j equals 2, let's try to compute a numerator for both cases. So for each case, for example, taking the example of j equals 1, we know that the numerator is p1 from the last iteration. So the first and the p value here times the normal density feeding in the corresponding old mu and variance. So, and the second one, so when j is equal to 2, this numerator is equal to 1 minus p times the normal density of xi given the old mu2 and sigma squared 2. So this can be obtained by doing vectorized operations, which is the product of the entry-wise product of the vector p and 1 minus p, the two possible values of p's, j equals to 1 and j equals to 2, times the vector of the two normals. So fxi, given that it's the first normal distribution, plugging in the old mu and variance, and fxi given the second normal distribution. So this can be obtained by doing denorm of x, where x is a single scalar, but mu's and square root of vars are the corresponding length 2 vectors of the means of the two normals and the standard deviation of the two normals. Once we get the numerator, we can see that the denominator for both j equals to 1 and j equals to 2 is the sum of these two terms inside this new vector. So this conditional probability is going to be equal to the numerator divided by the sum of the numerators. And it's going to give us a vector of length 2, where the first entry is the conditional probability that yi is equal to 1, given xi and theta old. And the second entry is probability that yi is equal to 2, given xi and theta old. Now we're ready to implement the EM algorithm. Let's run the EM algorithm for 500 iterations. In each iteration, we will start with computing the probability that yi is equal to j, given the observed data xi and the theta old. We will try to do this for each I from 1 to n, and try to obtain a n times 2 matrix, where each row is a sample and is an observation, and each column, the two columns correspond to the case that j equals 1 and j equals 2. In this matrix, we store the probabilities that yi is equal to j for each j equals to 1 and 2. We can do this by transposing the result of supply of x, where x is the vector of observations we get. So in this case, it's the length 1000 vector. We will try to apply to each entries of x, so each of our observations from 1 to 1000, the function py that we just created for computing this probability. Plugging in the values that p is equal to p old, the old p value we had, Mus is equal to mu old, and vars is equal to sigma square old. These are, at the current moment in the first iteration, the initial values. The resulting p-wise matrix, which contains these conditional probabilities, will help us try to find the maximizers of the Q function. So the first thing we can do is to update p old, so essentially get p new. In this case, we have seen earlier, the value of p that maximizes the Q is going to be the mean of the p's in the first column. So because we just have two classes here, so we know that the sample mean of the first column, which is the first class, will give us the p, which is the probability that someone comes from the first group. Then we can try to update the mu1 and mu2. Before doing this, let's try to compute the sum over all n's, the p's times the x. So if you recall, this is this summation over here. So let's try to get this numerator first. So let's denote it by xxp. And this is given by the column sum of the p-wise matrix, which is the probability that each of the observations takes value, each of the yi's takes value 1 or 2, conditioning on the current theta and xi, times xi. So this is going to give us a length 2 vector. And the first entry is the sum of the first column of this. So the sum of the product of xi's with the probability that yi is equal to 1 given the observed data and theta old. And then the second entry is the sum of the xi's times the second column. So the probability that yi is equal to 2 given the xi and theta old. Once we get the numerator, we will compute the updated values of mus. So this is given by sxp divided by the column sums of the p-wise. And then we can update the variances, so sigma square 1 and sigma square 2. So we know that this is given by the ratio seen over here. So the sum over all i's, the product of xi minus mu j squares times this probability, divided by the sum of pyi equals j given xi and theta old. So again, let's compute the numerator first. And before that, let's try to get xi minus mu j squared for j equals 1 and j equals to 2 for each of the observations. So let's create a matrix called square depth. The first column of this matrix is going to be xi minus mu1, the old mu1 squared, for each I from 1 to 1000. And the second column is going to be xi minus mu2 squared, I from 1 to 1000. So you can think of so you can see that the square depth matrix is also going to be a 1000 times 2 matrix. And then we can compute the numerator, which is given by the column sum of pys, this matrix, times this matrix. And then once we get the numerator, then we'll be able to update the sigma squared value with the value of theta of sigma squared that maximizes Q. And this is given by this numerator we just computed, divided by the column sum of the pys. And this is going to give us a length 2 vector as well, where the first entry is the new variance of the first normal distribution. And the second one is this iteration's variance for the second normal distribution. So let's take a look at the results. Ideally, you should run this for enough iterations to remove the Monte Carlo error, or try to set the sample size larger. But here, let's just, so the EM cycle is going to take some time. So let's try to just look at the results for one replication. The P old from the last iteration is 0.17. So around 0.17, which is quite close to the true value of 0.2. Of course, there are going to be some random fluctuations. The mu old from the last iteration is 2.79 for the first normal, so around 2.8 for the first normal, and 4.87 around 4.9 for the second normal distribution. Let's recall that for the true parameters. So the true means of the two normal distributions are 3 and 5 respectively. So the estimated values using the EM algorithm are again quite close. And let's recall that the true values of the variances of the two normal distributions were both 1. And in this case, the sigma square old from the last iteration is given by 0.9 and 1.04. Which are also quite close to the true values. So this is just a brief introduction to the EM algorithm. There are other cases where the unobserved data, the Y's or the latent variables are continuous, where you will probably need to use Monte Carlo integration or numerical integration to do this. You might see more examples when you do applications of EM when you take a more advanced class.